Hi guys, in this video I want to show you another feature of the ULM generator. So far we were just using it for specifying an instruction set architecture, and it then generated for us a computer architecture, and we already could program this with machine code. We were, for example, implementing this cat program and this hello world program. Now in this video I want to show you that you also can specify some assembly notation for each instruction, and then use the generated assembler for writing programs in this assembly language. You saw that actually writing programs directly in machine code is not as hard as you probably have expected before. It just requires a bit of patience, a bit of discipline, and most of all a good memory. Because over the time we have created more and more instructions, and then you have to memorize all these opcodes. You have to memorize these instruction formats, and you have to memorize the meaning of the instructions. And providing an assembly notation helps you to keep track of this information, because you can use mnemonics in these notations for the instructions. And you can use this assembler as a stupid tool, which is doing something you could do by yourself, but you don't want to do anymore, because it's always the same thing, looking certain things up in this instruction table and writing together this bits in the right sequence into this executable. And in the demo, I will show you how to extend your instruction set architecture for this assembly notation, how to use this tool, and also some other features for things like figuring out how many instructions should I jump forward so that I jump to the hold instruction, or backwards so that I jump back to a certain instruction, reading in some character from terminal. And I just show you this by rewriting this cat program that we have in machine code into assembly code, and also this hello world program. For this demo, I will use several terminals. In every terminal you see, I'm in the directory of the ULM generator, and this terminal here I will use for making changes to this instruction set architecture that we defined, adding this assembly notation. This here I will use for showing you the machine code that we were creating in the last video. Here I want to show you how to rewrite this in the assembly code, and here I will do the examples, the runs. So in this last video we were creating this variant in the subdirectory hello. So here we have the instruction set architecture description, we have this program cat and this hello world program. So here I'm opening this instruction set architecture description, and here I'm opening the machine code implementation of this cat program. And now here I want to create a new file, also in this subdirectory where it belongs to. And this will be called cat.s. .s is the typical extension for assembly programs. And now I will begin with the first instruction in this program written in machine code. This had the opcode hex02. So this was this instruction here. And now we have to recall what this instruction was supposed to do. It was supposed to read a character from the standard in and store it in register X. So for making it easier to remember what this instruction is supposed to do, we give it a mnemonic. So I insert a new line below the opcode. I begin the line with a colon, and then I call this mnemonic get C, get character. I also want to use an operand, of course. I want to specify where to store this character, and I want to use this notation that the percent sign indicates that a register is used to store it, and the X is used to identify this register. So that's it. Now I regenerate the ULM, and it will also regenerate the ULM assembler. Now in cat.s I want to use this assembly notation for generating this first instruction. You have to know that assembly code is organized in columns. The first column is the so-called label field, the next column the mnemonic field, and the remaining columns are used for the operands. You see in my syntax highlighting, if I would type in here in the first column, that means at the beginning of the line, get C, it has this dark yellow. If I would type it now after a space again, it's green because now it's mnemonic. And after that, I could use actually get C as an argument, as an operand. So now I just will leave the label field empty. So I will use at least one white space, or in my case a cup. Then comes the mnemonic, and then comes the argument. I want to store things in register 1. So that's it. And now I can use the ULM assembler that was already generated in the build directory, in the corresponding build directory, and it's called ULM AS, ULM assembler. And I want to generate machine code from cat.s. And the output is called a.out for assembler output. And that was generated. Now you see here, this is the machine instruction that was generated from getC, and actually you see here a few more features of this executable format supported by the ULM, and a few of these features we haven't used so far. So for example here, this first line indicates that the following lines belong to the text segment, and this text segment should have an alignment of 4. And you also see that each instruction of this text segment has this address field, followed by the colon. It specifies to what address a certain instruction should be loaded. And by default, the first instruction gets loaded to address 0. And this here is just a comment. We already used comments before. You also see that we have a data segment and a PSS segment. Should sound familiar from this C by example series. And we have, in this case, an empty symbol table. Now, we will come back certainly to all these things later. Now, in this fashion, I want to create mnemonics for all the remaining instructions and then just rewrite this cat program into assembly so that I have a more convenient way to express it. And then you should see that this assembly description is equivalent to the machine code, just more convenient. That's the purpose of it. The next instruction had opcode hex05, so that's the instruction here. And I want to call this like it's called in the GNU assembler on my platform, subq. I'm subtracting quad words, 64-bit values. And I want to subtract the value of x from the register addressed by y and store the result in the register addressed by z. And then I have to regenerate here the assembler because we have a new mnemonic. And then I can use it here. And I was subtracting here x ff from register 1 and store the result in register 2. And this will generate this instruction. You can also use different representations for integers, for example, decimal or octal. So this should generate the same instruction from different representations of this integer. Of course, we just need one of them. Now the next instruction was this jump instruction, this conditional jump instruction with opcode hex07. And I want to call this, for example, now jump 0, because the condition is that the 0 register is set, and I want to jump certain instructions forward or backward. Now for using this instruction, recall that here we specify that if this condition is met, we want to jump forward 3 instructions. In the assembly code, you specify how many bytes you want to jump forward from the current instruction, for example, 12 bytes forward. If you want to have the same idea expressed in your code that you want to jump 3 instructions forward and each instruction has 4 bytes, then you also can use an expression here. For example, I want to jump 3 times the size of instructions forward if the condition is met. And you see that in both cases, again, the same instruction gets generated. The assembler knows that jumping forward means jumping forward a certain number of instructions. Each instruction has 4 bytes, and that this is encoded by this right shift by 2 is stated here. This is a jump offset field, so it always stores this right shifted bit pattern. So here we again just need one of them. The next instruction is this with opcode hex 03. It's supposed to print the character, and the character was stored in a register, so I will call this put C, put character, and the character is stored in register specified by X. Let's also do the next 2 instructions. I think you got the idea. The instruction with opcode hex 04 is an unconditional jump. I just call it jump, and the offset is again specified by X, Y, Z. And the last instruction that we use is this halt instruction. I just called it halt, and the exit code is in register X. Then we actually first should run make again, and here we now can complete the program. We want to print this character, then we want to jump back to the instruction with get C. So we want to jump back 4 instructions, so -4 times 4. And then we want to halt the program with exit code stored in register 0. And that's it. Now we can run this, of course, for testing it as before. And again, here I think the command line tool should do it. Let's stick to English. Control D is terminating the program. You see that writing a program in this assembly notation is a bit more convenient compared to this machine code implementation, but still equivalent to each other. There are actually a few things that we can do even better, even more convenient. What is still annoying is that for these jump instructions, we, for example, still have to do the computations by ourselves. Here I have to compute 1, 2, 3, 4 instructions backward. And actually I just want to jump to this get C instruction. And for that I also can give this label in the label field. Label basically the next byte generated by the assembler with G, and then I want to jump here to this byte generated after this label, which will be this get C instruction. And here I actually want to jump to the halt instruction, so I use here a label H, and this is the label for the next byte generated after this label instruction. The assembler reads this line by line, keeps track of how many bytes were already generated. Counting starts at 0, so this here will have the value 0, and this is also the address of the next instruction. And this H is the label after 1, 2, 3, 4, 5. That means 20 bytes were generated, so it should have the value 20. Let's see if this is actually the case. You now see that the symtab has some entries. The symbols are G and H. They are both located in the text segment, the only segment that we're using so far. G has the value 0 and H has the value hex 14, which is 20. And you also see that the same machine code was generated by the assembler. So the assembler did the computations for us. For example, here, it computed the distance from the current instruction at address 8 to the label H. The label H is the address of this instruction. So it computed the difference, also did this division by 4 for this efficient encoding. And the same thing happened here. From here, it had to compute a distance from this instruction in at address 16 or hex 10 to the address 0. And then, of course, was using the 2's complement for the signed integer representation, also did the right shift. So this is already much more convenient. What is kind of annoying is that I'm just using single characters for these labels. And I did that because this column for the labels is so small in my case. Of course, I could rearrange the code so that I can use more characters for the label, but that's inconvenient to resize things based on how many characters you want to use for a label. You can actually use a single line for a label. If the label is followed by this column, this indicates that there is no instruction in the same line, but the value of this label is as if you would use it in the next line. And so I will do this also here. Of course, usually it's maybe not a good idea to use the same identifier for the label as you have used for the mnemonic. But here there's no confusion. I mean, also in the code, I always said that here, for example, I want to jump to the halt instruction. So in this case, I think it's actually expressive. And here I want to jump to the get C instruction. And for the assembler, there is anyway no confusion. If something is found in the label field, it's always an identifier for a certain address. If something is found in the operand fields, it's also clear that it's not meaning a mnemonic, and only if something is found in the mnemonic column, it should be a mnemonic. Otherwise, you will see there will be an error message if you, for example, do a typo here. Okay, now let's see that we again have the same machine code actually. The machine code is the same. Of course, the symbol table changed. Now the symbols are called getC and halt, but they have the same value. One more thing is still annoying, that I, for example, here hard-coded the bit pattern for our end of file byte. Actually, I want to write this like that because then the meaning of this byte, that its meaning end of file, is more expressive. And for that, I want to have in a symbol table a simple end of file with the value hex ff. And here I want to show you that you can use assembly directives. This .eq means that you can specify a symbol like end of file being equivalent to the, in this case, bit pattern hex ff. And of course, you also can use here decimal or octal representations for this literal or expressions. And now this is much more like how I like it. And then you see a new symbol is in the symbol table, an absolute value, and having this value. And the assembler was replacing this here, this end of file with this here. You see that this .eq directive was not specified in the instruction set. It's already built into the assembler. And another term for assembler directive is, by the way, assembler pseudo instruction. And the difference to assembler instructions is that a pseudo instruction or directive changes the default behavior of the assembler. For example, here, the default behavior of translating assembly notation into machine instructions was changed to add a symbol to the symbol table. And you see that from this no code in the text segment was generated. All these directives begin with a dot. On the website, of course, you find a complete list of these directives. So it's not in general a good idea to use mnemonics that begin with a dot in your instruction set. You can do it if there are no name conflicts, but yeah, matter of taste. I wouldn't recommend it. As I said, there are also other directives. And for the Hello World program, for example, we will need this .string directive for generating some ASCII code for a certain string literal for Hello World And this will generate a zero terminated string representation in hexadecimal. Let me also show you another one already. .byte generates a byte representation with a certain value, for example, for 42. And then you see here this generated this in the text segment. And this here is the zero termination of the string, followed by this hex representation of 42. Another directive that we will use is the .data directive. And this will mean that after this line, code should be generated for the data segment instead of the text segment. Let me first show you how this changes the output here. Now you see that now this bytes generated from this .string and .byte directive are now in the data segment. Actually, now I don't need this window here anymore, and then I can make this a bit bigger. And the nice thing is that you can change the position of this data segment in your assembly code. For example, I often prefer it to have it in the beginning. I first want to specify my data and then write code for using this data in the text segment. So by that I specify first the data segment and then the text segment. Of course, the assembler knows that in the end, executable should be consisting of the text segment followed by the data segment. And it will reorder things as they are needed. And you see that here. Same thing. It doesn't matter where you begin the data segment. It will actually even keep track of splitting it up like that. Then you specify the first part of the data segment, then some part for the text segment, then you switch back to describing the data segment, and this is what gets generated, the same data segment. Now let me clean up here this mess. Actually, this is supposed to be just a cat program, but you saw that I'm already ready to begin with this next example of the Hello World program. And for that I begin with the machine code. Let's copy this. And I just copy paste this machine code in here. For some instructions we already now have some assembly notation. It's missing, for example, here. This is supposed to jump if the zero flag is not set. So it's a jump not zero instruction. X, Y, Z. Actually, I also can give here more than just one possible notation. Sometimes I also want to call this jump not equal instruction. And then I give here an alternative. Here I also want to call this sometimes jump equal instruction. And in your assembly code you can choose what notation you prefer. Now this instruction here I want to call load a register with a certain bit pattern with zero extension, and I have to figure out some more compact, more convenient name instead of such a long name, and I will call this load zero extended word into a quad register instruction. LDZWQ. Well, okay. You have to choose some kind of shortcuts. Otherwise you get crazy if you have to write so much. So I want to change this zero extended bit pattern of XY into the register set. And this fetch instruction. Here I want to use a name that is also used by the GNU assembler on my computer. I want to move. Actually, it's a copy, but in the assembler it's called a move instruction. I want to move a 0 extended byte into a quad register from a certain memory location. The memory location is specified by register X, and I don't want to write this like that, that I want to copy something from this location. I use also this GNU assembler notation where I put it in parentheses, and then this indicates the memory cell with the address specified in register X, and this should be copied or moved into register Z. And here I want to add some immediate value X, so I also use add Q for doing computations with quad words. So I want to add the immediate value X to the register Y and store the result in register Z. And here we actually don't need that for the Hello World program, but just for completeness, I want to multiply in 64 bits, and my assembler calls this an integer multiplication with quad words. So I mul q, to distinguish it from the 128-bit multiplication. So these are just conventions that I borrowed from somewhere else and adapted it to the ULM architecture. Okay, but now this is complete. And I think now you can see all of the assembly notations. And now I go back to the Hello World program. Okay, I want to load an address of a certain character into register 1. And so that means I load a 0 extended word. I hope that the address fits into a word, into a quad register. What address? Well, the address of some string, which I will identify with a label message. Into a register. Well, let's use the register 1 for that. Now, of course, this should be the address of this string down here. And so this will get the label message, and it should generate this bytes from this string literal. Now, here I actually already changed my mind. I don't want to call it explicitly register 1. I want to call it the address register, the register which stores the address. So let's change this to that and define some symbol for that, so that address is the address is stored in register 1. Now we're done with that. Then I want to fetch from this address some byte into a register. So I use my move 0 extended byte into quad register. I want to fetch it from this register where I stored the address and store it in the register where I store the character. Let's call this register CH for character. And I specify here another symbol. And we're done with that. Now here I wanted to check whether we have this 0 terminator, the symbol for marking the end of the string. So I'm doing a subtraction of 0 from what we have in this register which stores the character. And I want to store this into the 0 register. Okay, so that's this here. And then I want to jump if this was 0 or if it was equal to 0. So I can use here jump 0 or jump equal. I want to jump to the halt instruction. And that's it. I just have to remember that I should use this label halt for the halt instruction later. And in case we didn't jump, the next instruction should now print the character. So put C, this character stored in %ch. And then we have to increment the register, keeping the address. So I use my add queue instruction. I want to add the immediate value 1 to this register that stores the address. And this should be the value afterwards. So I store it into this same register again, and that's it. And then I want to jump back to fetching a character. So unconditional jump, how should we call it? Well, load, for example, or fetch. And that would be here. That's it. And now we have the halt instruction. And that should do it. I didn't use this .data.text directives. This is my first version. Now I have to regenerate the assembler because I changed here a few things. And actually, I wish I would have done that before I wrote this assembly program to make clear that I'm now just regenerate this assembler, but I'm not translating somehow this assembly program. So I could first have created this new assembler. Then I can use this assembler as long as I don't change the instruction set and the assembly notation. But anyway, now we have this new assembler. That's this one here. And now I want to translate this hello.s. And then we can run this created a.out on the computer for this architecture. A.out, hello world. And you see also that this was generated now by the assembler. You see that we just have a text segment. And if you look at the actual bytes of this text segment, they are identical to this bytes from our Hello World program directly written in machine code. We have here in addition these addresses, but these bytes are stored to exactly the same addresses as before. This is just showing the default behavior of loading this program. We of course have in addition this symtab, because we were using certain symbols, and we have this so-called fix-up table. The symbol table and the fix-up table will be important when we deal with generating just object files from assembly code and then linking together these object files. For now, you will see that they are actually not needed. Let me remove a few things. Actually, everything after the text segment can be removed in this case. The data segment and BSS segment is anyway empty. And the symtab and fix-up table, as I said, is currently not important. So let's delete that. Actually, we also can delete this here, indicating that the text segment should be loaded to a address which is a multiple of 4, because it will be loaded to address 0, which would be the case here. And that means I also don't need this addresses here, because this is anyway how it would be loaded, and you saw that comments are anyway ignored. And then you see it's still doing the same thing. Just to convince you that no magic is involved in this fix-ups in this program. Now let's also use this .data and .text directive up here. I want to have this actually in a data segment in general, and this data segment I sometimes want to have here, for example, or after this AQs here, or just to make clear that I can actually put it pretty much everywhere I want. I put it between these two AQ directives, and this here then marks the begin of the text segment. And the assembler still reads this line by line. The first line indicates add something to the symbol table. This here indicates now I described the data segment, create some bytes from this string for the data segment, also add this symbol to the symbol table. Now I describe to you the text segment, generate the machine code for this instruction, and so on. You get the idea. And when we now look at the generated output of the assembler, of course I have to make sure that I'm using the right variant for this instruction set. And now you see it's looking a bit different. We now have a text segment. We also have a data segment now. And as before, we have this symtab and this fix-up table. In this case, you also see that the data segment immediately follows the text segment. The specifier indicates that the data segment should be at a multiple of 1 in the address space. And this is, of course, the case for every address. So if the data segment has to follow the text segment and should be aligned to 1, it means it follows after this halt instruction immediately. And you will see, depending on what data is generated for the data segment, it might be different. If you generate a quad word for the data segment, usually you need an alignment of 8. And then here, this also would be the case, but sometimes it requires that some gap is between the text and data segment. Now here again, I can show you that just this text and data segment is actually needed. So let me remove here everything after that. And then you will see it will just run the same. And also you can run it in the debugger, and you see that it immediately loads this hex 68 after this halt instruction into the memory. Okay. Now let me also show you some typical error messages. If I mistype some mnemonic or pseudo instruction, it's actually already detected by the lexer, because in this column you either expect a mnemonic or a directive. If I, for example, remove this L, it's neither. So we would expect to get some error from the lexer, and actually it was detected by the lexer that it is a bad token, but then the parser got this token and finally generated this error message. So this is kind of clear. This means that you somehow have to correct something in this column. I actually also could generate some syntax highlighting description for Vim, so that if you mistype something in this column, you would see it from the syntax highlighting. But then the syntax highlighting would depend, of course, of this instruction set that you specify. That means for each of these variants, you would have a different syntax description for Vim. So this kind of error is easy to detect and understand the error message. Now, the next error would be, for example, having here 2 commas instead of 1. And this is a syntax error, of course. And then you see the parser complains that in line 9, column 17, that's exactly here, some percent was expected, but a comma was found. So in this case, it's also easy to fix. You exactly know where something was expected and what was wrong. But now assume that you, for example, forget this comma at all. But now let's read this error message carefully. Some comma is expected, okay, that was kind of clear, but at line 9, column 25. And that would be the character after this R. That's a new line. What was here detected by the parser? First in this line, this mnemonic was detected. After that, some expression is expected for the value that you want to store in some register. And now here we have a symbol followed by the percent operator followed by the symbol adder. And this percent operator, like in C, is the reminder after a division. So this here is a valid expression. But after this expression, some destination register was expected. So if you would have, for example, written here, percent, let's say 2, then this would be syntactically correct. Semantically not. As you will see, there will be a different error message now, but this is not a syntax error. Illegal expression. Reason for that will become clear later. This here is a symbol for the data segment. This is a symbol with an absolute value, and for that this kind of operation is not allowed. That's why it's illegal, and maybe I should provide better error messages for that. But nevertheless, you see some rule of thumb. If we go back to the case into which we run in the beginning, probably more frequently, maybe forget this comma, and how to use this reading of error messages also for C. Then you see if you get an indication that something wrong was detected here, it means that here or before something went wrong. So usually you start with this location, and from here you read your code backwards and see if there is some obvious syntax error. Now another thing, and this will be the hardest part of programming in assembly and understanding problems, is the case where you don't get an error message. Let's say we mistype this simple message here. And then you would expect perhaps some error message, undefined symbol, something like that. But none of that actually happens. If you would try to run the executable and there was some assembler output generated, then you get from the program loader actually some error message. Program contains undefined symbols, because now it generated an object file. That means machine code with undefined symbols. And if you look at the generated assembler output, you see that in the symbol table, we have here this symbol SG, which has the indication that it's undefined. So this is an example where you sometimes would wish to get an error message, because sometimes this happens that you mistype symbol names, but sometimes you need this feature that undefined symbols are allowed in assembly code. And in this case, the tool cannot help you. You have to look into the symbol table if it is containing undefined symbols that were not intended. That's it for this video. A few things that I just mentioned briefly in this video, for example, the format of these executables, are described in more detail on the website.